Here we finish our chapter with the bucket sort. So actually the bucket sort also, as the counting sort, it runs in linear time, and it is actually of order n. And actually it assumes that the numbers inside the array are in the interval 0, 1, and they are uniformly distributed. So it says, okay, given that all the numbers, given that we have actually n numbers or n elements inside the array, and all these numbers are between 0 and 1, then actually it will do the following. For example, let's start from an example, the array A, where n is equal to 10, so we have 10 elements. The first is 0.78, 0.17, 0.39, 20, 26, 72, 94, 21, 12, 23, 68. So the first step is we will create an array B, and B actually is going to have 10 elements. Why 10? Because actually n is equal to 10. And then what we are going to do, so each element actually at B will represent a list, like let's say a linked list, okay? And so all the elements in the first interval, let's say for example here from 0 to 1 we divide it into 10 intervals, so the first interval will be from 0 to 0.0, let's say from 0 to 0.099. The next interval will be from 0.1 until actually 0 to 2. Okay, let's say the first interval will be from 0 to 0.1, but 0.1 not included. The second element, sorry, the first element from 0, actually the first element will contain is a list, a linked list that contains all the elements from 0 to 0.1, okay, but 0.1 not included. The second element in B will contain all the elements, so it is a linked list that contains all the elements from 0.1 to 0.2 not included. The third element in B is a linked list that contains all the elements from 0.2 to 0.3 not included. The fourth element from 0.3 to 0.4 not included. The fourth element, the fifth element from 0.4 to 0.5 not included at the rate. And the last element in B is a linked list that contains the elements from 0.9 to 1. Okay, so as a result, after applying the bucket sort algorithm that we are going to explain after this example, we will get here, for example, what are the values from 0 to 0.1? None of this value is between 0 and 0.1. That's why this linked list is actually empty. Then, what are the values from 0.1 to 0.2? We have 0.17 and then 0.12. Okay, so we'll put actually in this linked list will contain the 0.12 and 0.17. Okay, so at the first step they are not ordered, it just contains these two elements. Next, what are the elements from 0 in this interval from 0.2 to 0.3? We have 0.26 and 0.21 and 0.23. So we'll have these three elements in the linked list at 2 here, at index 2 in B. We continue in the interval, the fourth interval from 0.33 to 0.4. We will have 0.39, and that's it. Okay, so we'll have only one element. The fifth interval from 0.4 to 0.5, there is nothing. From 0.5 to 0.6, also nothing. From 0.6 to 0.7, we will have actually 0.68. Okay, we'll have only one element. And then the next interval from 0.7 to 0.8, we will have 0.78 and 0.72. So two elements in this linked list. And the interval from 0.8 to 0.9, there is nothing. And the last interval from 0.9, from 0.19 to 1, there is this element 0.94. Okay. Now we have this array. We say, okay, we know that this array is sorted, but the linked lists also should be sorted. So what we will do, the next step, once this array is built, the next step is to say we'll go over each linked list and sort this linked list. Okay, and that's how the algorithm works. So I will say, okay, n is the length of the array, Then for I equal to 1 to n, we insert ai into list b in ai. Actually, what does this mean? This means the lower bound. So if, for example, let's say ai is equal to 0.4, so and n is equal 10, 10 multiplied 0. Let's say, okay, ai is equal to 0.45. So 10 multiplied 0.45 will give us 4.5. The lower bound is 4. So it's like to say we'll place the 0.45 at the interval with index 4, which is this one. Okay, this is the meaning of this expression. So we'll insert actually first AI into the list, into the corresponding list. And then we say, okay, now we will go over all the lists and and sort them using, for example, insertion sort. And at the end, we will concatenate the list b0, b1, bn minus 1 together in order, so we get a sorted array. Okay, so this is actually an explanation of what we said. And then here in the performance analysis, actually what we get, it is the average perform, because if I ask about the worst case actually will be when all the elements, for example, will be in only one linked list. And then to apply in one linked list the insertion sort, the linked list will have n elements. Insertion sort of n elements will give us n squared. Okay, so if the elements are not uniformly distributed and they are all in just one interval or in one linked list, it happens just that they might be, for example, all the elements between 0.5 and 0.6. So this is actually the worst case where we will get actually a performance that are n squared. However, bucket sort, it only applies in the case that the elements are uniformly distributed. This means that the probability to get an element between 0 and 0.1 is the same as the probability to get an element from 0.1 to 0.2 at its rate. Okay, and the performance actually is, if we calculate the average performance given this uniform distribution, we'll get that the complexity or the running time is theta n minus this value, which is equal to 2 minus 1 over n. So for n equal to infinity, or for n very large, this is like 0, and this becomes a constant, and then the performance are of order n. And that's everything for this chapter. Thank you for your attention, and I'm waiting for your questions in the discussion session. Thank you very much.